Hi, this is our project regarding LLM speedup using various methods, which we'll be talking about.
All right, so let's start with the dynamic pruning. We implemented a novel pruning algorithm where instead of a standard pruning based on the gradients or a purely random pruning, we wanted to prune based on the actual usefulness of the neurons. So what we did is we implemented effectively a ranking choice of an array of masks for various chunks of the model. And then by evaluating how much the various neurons inside the mask affected like performance, you could figure out which masks are the top 20 best performing masks effectively by doing an evaluation on the mask. And then by taking the top 20 masks and then finding the correlating neurons with the neurons which they all delete together, you can make that your final mask. So by using this random like spread, you can effectively like survey the entire model very efficiently. Like for quantization, we wanted to do something where we would take into account hardware at least at a simple level to figure out which quantization would be best. We implemented a couple quantizations, like an FP16 or a BF16 quantization, and also an 8-bit integer quantization.
Okay, now on to the third improvement. We wanted to improve the chain of thought management. And so the way we did that was we took inspiration from this paper here. And the idea is that we would train a smaller model, and then the bigger model would recurse on the smaller model to help give it more context to better improve its resulting output at the end. And so what we did was we trained a custom 70 million parameter model, which we built completely from scratch, and trained it on 1.4 billion tokens, which we got from the two data sets, Tiny Stories and Slim Pajamas. Um, and this, right, as you can see, is the algorithm that we used for the recursive loop, where we recurse between the larger model and then the smaller model, while also running the gradients through smaller model to make sure that we're learning how to create the context for the larger model to produce better outputs. And so, yeah, the pre-training is how we went about training the smaller model, as I explained earlier. Now we'll go into the post-training.
For the post training, right, we primarily focused on fine tuning so that to specify the model to the task that it needs to do, which is taking the prompt and some of the steps of the chain of thought reasoning and condense them together into less tokens and also provide a more enrichful prompt effectively back into the model that includes some of those chain of thought reasoning steps. And we took a data set, the open thoughts data set, which was graded using like a prompted Qwen3 model to generate long chain of thought reasoning. And we provided that into the model and then used the reinforced policy gradient backprop system to train the model because it's not directly interacting with the output.
Okay, now for the results. So some disclaimer that we wanted to create mention beforehand was that we noticed there's a difference between various the hardware components. So for example, Intel chips versus silicon, the M2 silicon or the M series silicon creates a difference, as well as even plugging in your laptop versus not plugging your laptop, where you notice a big difference in speed up. And so yeah, we can see a speed up here between different models, where we have the quantization pruning plus the SVD, and then quantization plus pruning plus SVD, and then the other way around. And we wanted to see which one created the best speed up. And so we have these results here. And then so for the future steps, we wanted to so for this model we focused only on the QN model, but we realized that we should be model agnostic, and so branching out and generalizing to other models is also really important. And also, we wanted to make sure that the fine tuning is complete, so that because we see a very big benefit in fine tuning a smaller model, and we feel like it'd be valuable to the overall efficiency in improving the context chain of thought. Yeah, thank you.